Hello, in this video I'm going to work through a few proofs using mathematical induction for finite arithmetic series. And so in this first example we want to prove that the sum of the squares of each consecutive integer here up to the nth term is equal to n times the quantity n plus 1 times 2n plus 1 divided by 6. And so we need to first prove or show that this is true for n equals 1. So we need to show n equals 1, in which case we have just 1 squared. We get the last term there, and that is all going to be equal to 1, just substituting 1 for n, 1 plus 1, times 2 times 1 plus 1, all divided by 6. And so we're going to carry out our arithmetic here. We've got 1 times 2 times 3 over 6, which equals 1. So that's true, check. And so our second part here, we're going to prove that it's true for n plus 1. So the series or the sum of all of those for n plus 1 is going to be equal to that series here plus, at the end of it all, we're going to have n plus 1 squared. So again, we're just going to substitute n plus 1 for each n. And so this is basically just arithmetic and algebra. And so we're going to have our, on the left-hand side of the equation, we're going to substitute n plus 1 for all of these values here. N plus 1 times quantity n plus 1 plus 1 times 2 times n plus 1 plus 1 over 6, and that's going to be equal to n times n plus 1 times 2n plus 1 over 6, and then we're going to add to that again n plus 1 squared. Alright, and so now we just need to do the algebra. So we've got n plus 1 times n plus 2 times 2n plus 3 over 6 is equal to n times n plus 1 times 2n plus 1 over 6. And then we're going to add to this side. We're going to get a common denominator, so we can get rid of the denominator. 6 times n plus 1 squared over 6. And so we end up getting, let's carry out, get rid of that denominator there. We get n squared plus 3n plus 2 on one side. Just using the FOIL method of expansion there. And then we got 2n plus 3, and that's equal to n squared plus n, again just distributing that n to that first set of parentheses there, times 2n plus 1, and then that's plus 6 times n squared plus 2n plus 1. And now it's just algebra from here. We're going to distribute, carry out FOIL, or multiply these two sets of parentheses by one another. We get 2n cubed plus 6n squared plus 4n plus 3n squared plus 9n plus 6. Then we're going to have to combine like terms here, and that's all equal to 2n cubed plus n squared plus 2n squared plus n plus 6n squared plus 12n plus 6. Again, combine like terms, these here and these there, and we end up getting 2n cubed plus 9n squared plus 13n plus 6 is equal to itself 2n cubed plus 9n squared plus 13n plus 6, and so that checks out. That is true. Let's do another one. So first we need to show that it is true for n equals 1. If n equals 1, then we have this value here, 1 times 1 plus 1 is equal to 1 times 1 plus 1 times 1 plus 2 over 3. And then we end up getting 1 times 1 plus 1 is equal to 2. 2 is equal to 1 times 2 times 3 over 3. Those cancel out. Check, that is true. Now we need to look at for n plus 1, so we're looking to say the series, the sum of that series, n plus 1, is equal to the original plus n plus 1 times n plus 1 plus 1. Again, we're just substituting n plus 1 for each n there. And so from here on out, we're going to take this, substitute n plus 1 for each n plus 1 times n plus 1 plus 1 times n plus 1 plus 2 over 3. And that is equal to, so we have the original series, n times n plus 1 times n plus 2 over 3, and then that's plus, let's see if I can squeeze it in here, n plus 1 times, n plus 1 plus 1. And it's just arithmetic and algebra from here on out. We're going to just simplify here, n plus 1 times n plus 2 times n plus 3 over 3 is equal to, and then on the right hand side we've still got that n plus n times n plus 1 times n plus 2 over 3, and then we're going to multiply this by 3 over 3 so we can get a common denominator to get rid of n plus 1 times n plus 2 over 3. We get rid of all those denominators and we end up with n plus 1 times n plus 2 times n plus 3 is equal to n times n plus 1 times n plus 2 plus 3 times n plus 1 times n plus 2. And so here we see we can use the distributive property there, and we're going to rephrase that right hand side. We got n plus 1 times n plus 2 times n plus 3 on the left, and on the right we can say n plus 3 because we got n over here, and then we've got an addition here, and we've got the same two values in this term here as in this term, so we can say n plus 3 as a quantity times n plus 1 times n plus 2, and then these cancel out. We get n plus 3 equals n plus 3, so that is true. Right. On to the next one. So prove that, prove that the sum of all odd integers starting with 1 is equal to n squared up to 2n minus 1. Alright, so looks intimidating maybe, but let's just first say n equals 1, and we're going to solve for n equals 1. If n equals 1, then we've got, just going to take this last term here, we're going to substitute n, and we get 2 times 1, substitute 1 for n, 2 times, yeah, that was right, 2 times 1 minus 1 is equal to 1 squared, and so we get 2 minus 1 equals 1, that's a check, it's true for n equals 1, and so then we can go and check if it's equal to, if it holds true for n plus 1. If it does not hold true for n plus 1, then the series is false. S sub n times 2, and then we're going to substitute n plus 1 for each n. And so the series at n plus 1, we're going to take this right-hand side of the equation, and we're going to substitute n plus 1 for each n. So instead of n squared, we've got n plus 1 squared, and then we've got the original value here, the original right-hand side. We're going to add to that this value here, which ends up being 2n plus 2 minus 1, or 2n plus 1, however you like it. And so let's expand this. We get n squared plus 2n plus 1 is equal to n squared plus, we can get rid of that parentheses there, 2n plus 1. So that's a check. That checks out. Last one, we're going to prove all of this. The arithmetic series, the finite arithmetic series, looks like 1 over each consecutive integer times 1 plus that integer, or 1 over n times n plus 1 is equal to n over n plus 1. So first let's see if it's true for n equals 1. And we're going to plug that in just in that last term on the left, see if it holds true for n equals 1. We've got 1 over 1 times 1 plus 1, which equals 1 over 2, and that's equal to 1 over 1 plus 1, so that is true. See if it holds true for n plus 1. So S, the series, n plus 1 terms is equal to the original series plus, and then we're going to take that last term here, and we're just going to substitute n plus 1, 1 over the quantity n plus 1 times n plus 1 plus 1, or n plus 2, right, and then start working it. So we've got on the left-hand side, we're going to take that original right-hand side and substitute n plus 1 for each n. So we've got n plus 1 over n plus 2, and that's equal to the original series, which was n over n plus 1. We're going to add to that this value here, 1 over n plus 1 times n plus 2. And then we're going to get a common denominator by, well, we don't need to do that first part. We're going to multiply that first numerator by the first part of that second denominator in order to get a common denominator on that right-hand side. So we get n plus 1 over n plus 2 is equal to n, we're going to multiply it by the second part of that second denominator, n times n plus 2, and then that's plus 1 because this fraction already has both parts of our common denominator, which is n plus 1 times n plus 2. Right, we're getting there. And so let's look for common denominators. Let's look to make a common denominator again. And so we can multiply this fraction by n plus 1 over n plus 1, which is the same as multiplying it by 1. So we get n plus 1 squared over here, over n plus 1 times n plus 2. And that is equal to, let's distribute this n here. See if we get the expansion of this here. And in fact we do. And so this holds true. Right, so for finite arithmetic series, if you want to prove that it's true for any n, or if you're looking to prove that your given is equal to what you expect to be your general rule as a sum, then you're going to substitute each n plus 1 for n, take the right-hand side, move it over to the left, substitute n plus 1, and then take that same right-hand side, make that the first term on the right, and then add to that your substituted value n plus 1 for each n for that last term there, after you show that it's true for each n equals 1. Okay, I'll do a few more examples of math induction in the next video. Thank you.